So the last way that we're going to learn how to estimate definite integrals is actually our most accurate way, but it also is probably the toughest of the different ways of estimating. So we started with rectangles, RAM, very easy to calculate, but not very accurate until we go to a lot of rectangles. Trapezoids, little bit more effort to calculate, not too bad though, uh, but offset by the fact that with the same number of shapes as rectangles, it's more accurate. Well, then Simpson's rule is actually very accurate. It just, with a very few number of shapes, it just takes uh, some effort in as far as to remember how to do this. So the idea of it is if we have a region, and say we were looking at this graph, and I wanted the definite integral from 0 to whatever value this is. We have to divide it into an even number of partitions or subintervals. So let's say I divide it into 4, because that's what we've experimented with rectangles, with trapezoids, and all of that. So if we do that, the difference here is we're not using quadrilaterals in order to estimate the area. We're not using rectangles, we're not using trapezoids. What we're actually doing is within one partition, we're actually fitting a piece of a parabola. So it could look like this here, it could look like this right here, it could look like that here, or this here. And this is actually very, very efficient. Now, I'm not going to go through explaining and proving where this formula then comes from that finds these areas. But the way it works is if h is b minus a over n, in other words, the length of one partition on the x-axis, or the width of one partition, we take that divided by 3, and then we're going to multiply it by, in this case, this would be y0 plus 4 times y1 plus 2 times y2 plus 4 times y3, and then plus just 1 times the last one here. The key is in the middle, so it's 1 times the first y value, 1 times the last y value, but in between it goes 4, 2, 4, 2, 4, 2, 4, 2, 4, and you just keep repeating that, but it'll always be 1 plus 4 times something plus 2 times something, and it always ends with 4 times something plus 1 times something. And it's because of this pattern that we need an even number of subintervals. So if you try to do Simpson's rule with 5, it's not going to work. So for example, let's say we wanted to approximate the integral from 0 to 2 of 5x to the 4th with respect to x. So here's a graph of 5x to the 4th, where at 0, y value is 0. At 0.5, the y value is 0.3125. At x equals 1, y is 5. At x equals 1.5, y is 25.3125. And when x is 2, y is 80. And if we divide this into 4 partitions, so these would be the partitions, then the estimate for our integral using these pieces of parabolas, well, I would need h, and h would be b minus a over n, which is 1/2. So that would be 1/2 over 3 times 1 times y1 plus 4 times our next y value plus 2 times the next y value plus 4 times the next y value, and then since I'm now at the last y value, I would do just the last one here. And so now, when I go through and actually calculate that, I would get that this integral is going to be about 32.083. Now, to give you an idea of just how accurate that is, if we actually evaluate the integral from 0 to 2 of 5x to the 4th, using antiderivatives, we would get 2 to the 5th minus 0 to the 5th, which is 32. So using only four intervals, we were within 0.083 of the exact value, which is amazingly accurate for such a few number of shapes.